Use case number 1 in Cilium SRv6 L3VPN discovery series of videos. Let's start with the transport network that is SRv6 enabled and has two customers connected to it, green and orange. Each has two locations, and the physical location with CE devices with some local area network connected with its upstream PE device. The BGP session is established between the CE with IPv4 family enabled, address family enabled, to advertise the local area network to PE, as well as effectively to get the remote local area network advertised via BGP via the route reflector. Each PE connects to a single route reflector, and that's where the VPN v4 address family is configured. And at the end, C11 knows the route to the other side local network. Exactly the same goes for green. That's our, let's say, legacy LSVPN setup across SRv6 network. Right now, the goal here is to add the data center. It essentially can be added anywhere, as long as we can connect it to either directly or indirectly to SRv6 backbone. In this example, in this use case, I have a data center that consists of 4 nodes, 1 control plane node and 3 worker nodes. It's essentially logically one single Kubernetes cluster. These nodes are connected via L2 switch to the upstream Tor device. So from the Tor perspective, there is a single physical interface towards the cluster, and all these nodes are part of the same of the single network, same broadcast domain. Once the servers are connected to the Tor, and then the other two configurations must take place. The BGP peerings must be established. One peering is between the Kubernetes nodes and the Tor. It is with IPv6 address family enabled, where we will see SRv6 locator being advertised, as well as we have another BGP session, the red one, going to the same route reflector while all the PEs are connecting to. That's where the VPN v4 address family will be exchanged. Keep in mind that from the L3VPN perspective, every Kubernetes cluster node behaves as a PE. In fact, it will receive IPv4 traffic from the applications running inside of the node, and upon forwarding the traffic to the outside world via the Tor, the traffic will be encapsulated with the IPv6 packets according to the VPN v4 advertisements SRv6 TLVs. So functional-wise, the Kubernetes node behaves pretty much the same as the iOS XR device or PE device. For that to happen, you will also see that we need to create a VRF, and we need to define the VRF in Kubernetes cluster, and then the applications, containers, or pods are deployed inside that VRF by using specific metadata label that will be pairing those applications with the VRF, and based on that, the forwarding behavior of the Kubernetes cluster will be changed, and effectively, we can deploy applications in orange and green VRF in the shared multi-tenant kube cluster. The success criteria, instead of using pings to prove that things are working correctly, there will be some cloud-native applications deployed or pre-deployed on the kube cluster that are configured to send the data to its to another device. It will be tbump agent deployed in kube cluster, tbump responder deployed on every site location. And the responder is very basic, the application that receives the packet and bounces it back to whoever was sending that. While the agent will try, as long as the connectivity is enabled, to send the traffic across the network to its own configured reflector. And when the traffic is returned, the delay is measured and sent via Grafana to InfluxDB and then visualized via Telegraph to Influx and visualized in Grafana. And that's what you will see on the demo instead of using the